Hello students, in continuation of the last module, we will now consider the performance analysis with respect to the general tone jamming. By the term general tone, what I meant to say is here actually the jamming signal, the presence of the jamming signal is considered to be anywhere close to the center frequency of the intended signal transmission, which is equal to Fc. It need not to be exactly coinciding over Fc. It is any general tone or any general carrier frequency where the jamming signal is present. How far actually the symbol error probability calculation for the intended signal will be now affected by the presence of the jamming signal on any general tone close to it, but not exactly coinciding with its own transmission frequency. That is the point of consideration for us. We will refer again the same block diagram which is for the match filter based coherent PSK transfer coherent PSK receiver we have discussed several times earlier, and we also understand again that the received signal model is given by RT is equal to ST plus IT plus NT, where ST is the intended signal, IT is the jamming signal and NT is the noise associated with the incoming signal. After receiving the incoming signal, the receiver has synchronized it to the carrier frequency and basically it has boiled it, it has brought it down to the baseband. The cheap match filter is designed such a way that the transfer function of the match filter is matched with the cheap waveform psi t. So, its transfer function is psi of minus t. Output of the matched filter is sampled by the sampler. Remember, the sampler and the spreading sequence generator, they needs to be in sync, which is taken care by the chip rate clock. Sampler is sampling the incoming match filter output signal at a rate of the chip rate, that is equal to 1 by Tc rate, and his target is to produce the capital G number of the samples, where G is given by the Ts by Tc. The basically G is the number of the chips available within the symbol duration, and this demodulated sequence at the output of the symbol, output of the sampler is getting multiplied with the locally generated spreading sequence, and here we saw earlier that we have generated the chips which generated the chips which is called the Zi after multiplication, and this multiplication combined with this adder is equivalently jointly actually offering the respreading operation in the receiver, and this is a correlator beta based architecture also as a whole, and this Zi when summed up over the G number of the samples, I mean I is varying from 0 to G minus 1 total G number of the samples, you will be after addition you will be ending up with signal V, which is entering at the input to the decision device, and decision device output we are interested to see the form of a V, basically the mean and the variance of the V, as we have seen in the last module in presence of the jamming signal, and he will be this mean and the variance of the V will be greatly actually affecting the computation of the symbol error probability Ps at the output of the decision device. So, decision device is basically identifying taking the decision over the transmitted signal, and whatever the error is coming out at the output of the decision device, we are computing the symbol error probability based on that. So, with the understanding of this, let us proceed. Remember, in the last module we have understood that symbol error probability will take a form of like this: Ps is equal to 1 by pi uniform integrated over 0 to pi Ps phi, where Ps phi was the symbol probability conditioned on the phi, and phi was the phase, relative phase of the interfering signal relative to the desired signal, and in continuation to this equation, we will revisit this equation basically for the new consideration of the interfering signal. And remember that for the effect to examine the effect of the tone interference with the carrier frequency, which is different from the desired frequency now, we will utilize a Gaussian approximation for the easy tractability of the mathematical derivation. And this is the new interfering signal of our consideration given by equation 1.31. Well, like the earlier case, our I will be the average jamming power. Remember, now the signal is transmitted by the jammer at f1, and f1 is not equal to my intended signal transmitted at fc, and theta 1 is the corresponding phase of this jamming signal. Remember, theta 1 is measured with respect to the desired signal, the phase of the jamming signal with respect to the desired signal. Though f1 is not exactly equal to fc, we will think that if this is my transmission frequency fc, f1 is very close to fc in such a way that the difference of this f1 minus fc, which we will define later on as fd, is much very less compared to your f1 plus fc. So, center frequency of transmission of the jamming signal, they could not it is given by f1 here, and the assumption is the estimation process of the transmission signal was not done correctly at the jammer by the jammers, and that is why actually because of this estimation errors he is transmitting and the frequency of f1. Another consideration is that see this when f1 is entering in front, actually we have seen that the RT is received by the transmission by the receiver antenna, and it is usually for all kind of the receiving antenna, the received signal is passed by a wideband filter, and then it is amplified, also passed to the low noise amplifier and then fed to the match filter. But remember that when this wideband filter was filtering the signal, the location of f1 is such that because of the closeness of with fc, this f1 was also passed through the wideband filter. So, wideband filter could not cut it out. So, in what sense it will cut it out is, if your difference between the fc and f1, if it is large, it may happen that f1 is falling outside the wideband filter bandwidth, and in that situation the effect of the f1 won't be at all in this kind of the mathematical analysis that we are worried about, and also in the symbol error probability it won't have any effect on that, and hence in this kind of situation that can be neglected. But here in our analysis we are considering that f1 is so close to the center frequency of transmission fc that wideband filter is allowing that f1 to enter into the baseband, and so it is completely undisturbed. So, f1 is also completely undisturbed like our desired signal frequency fc. And we have also already discussed that this consideration holds good, the difference frequency is very less compared to the f1 plus fc, and so that all the terms in this derivation which involves f1 plus fc, we will be neglecting them. We will refer once again that expression of the ji, because ji is a part of this zi. We saw in the earlier module that zi is constituted of si plus ji plus ni. It is the input to the adder circuit. This ji expression was given by this because it is the interference multiplied with the locally generated PN sequence waveform, and cos 2 pi fct was contributed from the front end of the receiver, and we were integrating it over one chip duration, and psi t was the chip waveform, and we will vary the chip waveform from rectangular to the sinusoidal in the later slides. But fundamentally we will now replace the value of this I t given in the previous slide into this equation to proceed further. So, j I, if I substitute the value of I t from where, from the previous slide that we have discussed this expression, and if I substitute it there and you do actually some change of the variables, especially substituting the small t as t plus I t c, we will be ending up here, and where actually this 2 is contributed because we have considered the 2 cos 2 cos a cos b. In order to consider 2 cos a cos b, we have entered inside the integral are 2 and that 2 came out also. So, we need to divide it by another 2, and fundamentally the point where we are ending up with is interesting part is here, where the contribution from the difference term of the two frequency is playing a good role. We have another term called theta 1. We will see little bit. Theta 1 is the phase, relative phase of the interfering signal with respect to the signal of our interest, and here another term is expected to come, which will be the contribution for the FD shift multiplied with the chip duration, and for the ith chip it is a function of I also. So, this section will be keeping on increasing when the I is also increasing kind of. So, fundamentally if I integrate this section, if I evaluate this integration and we simply apply some trigonometry, this one will be further solved by equation, solved to equation 1.33, where this is a sinc function and this cos 2 pi f d t plus theta 2 we will be ending up with, where theta 2 we will be replacing by this theta 1 plus I 2 pi f d into T c. In the next slide, we will be interested to compute the variance of this V 1. V 1 is the contribution. V 1 is where V 1, if you recall, after the adder circuit. So, Z I was the input of the adder circuit, where we computed the J I part contributed by the jammers. Output of this adder network, there was a decision device. Our V was here, where like J I, your Z I, your V will be also contributing 3 part. One is the contribution from the signal, then is the contribution from the jamming part, and the contribution from the noise part. V 1 is the contribution from the jamming part. So, we are interested to check the variance of V 1 and the mean part of the V 1. In order to compute the variance of V 1, as you have crossed the adder, so that J I that you have computed in the earlier slide, that square of it and the mean value of it, definitely this is a definition of the variance, it should be summed up over the G number of the samples. And now, if I substitute the value of J I from the previous slide, it will boil down here, where what we have done is inside that you have seen that we have a cos term, cos of theta 2 plus that 2 pi f d t c. Let us go back. Remember, here we have a term of cos 2 pi f d t plus theta 2 term, and then here squaring up that term will lead you to cos square theta, and if I add 2 cos square theta, it will be 1 plus cos 2 theta. So, based on that and summation over the G, that 1 will be turned to G, and here you will get that summation left over the cos 2 theta section. So, simply, and the remaining part is squared up, nothing else has been done. If I replace now this G by T s by T c, where T s is the symbol duration, and if I utilize the following trigonometric identity to evaluate this section, the summing section, where cos of a plus nu b is given by cos of a plus n minus 1 by 2 b into sin n beta by 2 by sin beta by 2. This trigonometric identity will be utilized to change, actually to compute this in a summation. We will be ending up this from equation number 1.35. We will be ending up from the equation number 1.35 to 1.37, where actually this summation T s is coming because the summation output, summing over all the number of the chips, the T c, the sum will end up with that T s, and sin square f d T c will be remaining, and this because of the addition of this trigonometric part, with this contribution will come down. Remember, here further substitution has been done mentioned by phi, because this phi is now the whole part, this theta 2 plus pi f d into T s minus T c, where this, if I substitute the value of this theta 2, which is, we understand that it is nothing but theta 1 plus pi f d into theta 2 is equal to theta 1 plus pi f d into T c, we will, this whole phi will be ending up with theta 1 plus pi f d into T s. So, This is the final variance term which where we are our interest is lying. Remember, if I give you the value of this phi, then the value of the zi, the value of this zi given by this equation or given by this 1.32 or 1.33 wherever you go, this is bounded. This is a uniformly bounded constant. They are the uniformly bounded, all the gi's are the uniformly bounded constants. Hence, whenever we are computing this vi, adding up actually over the multiplying with the pi and adding up over the I number of the samples, remember this won't be nu, this will be I is varying from 0 to g minus 1, and then they are the independent and uniformly bounded. They will be also uniformly bounded because the property says so. Since your variance v 1 can goes to infinity as g is tending towards infinity, so it will keep on increasing. By applying the central limit theorem, we can see that when g is really very large, so v 1 can be approximated by a Gaussian distribution, and thus if the input device the v, which is a combination of these three terms, we find that actually that this whole distribution will now go towards the Gaussian distribution. So, anyway this noise is having a Gaussian distribution, the mean value of it, and this guy is also now showing the Gaussian distribution for when g is really very large. So, we can say that this v will be also Gaussian distributed, where actually the mean value of this v will be approximated to this and the variance will be this plus this. Remember, the mean value of this jamming part will be again 0, because with the constraint discussed in the earlier module, the v 1 is having the mean 0 value and is having some variance. Here we have whatever we will be interested next is the computation of this variance of both of them and checking actually the effect of them on the error probability computation. And as we understand that there is a symmetry in the model, then hence the conditional error probability may be calculated by assuming d 0 equal to 1. So, whatever the conditional probability we will be ending up with considering d 0 equal to 1, it will hold good also for the d 0 is equal to minus 1. And we will try to evaluate the probability that v is less than 0, because that is the situation that you will get an error given transmitted data was 1. So, your decision device will give a wrong indication when you have transmitted 1, but it has seen that the input is less than 0. It will not be able to detect d 0, he will decide that as if the transmitted data symbol was equal to minus 1, which is wrong. So, hence the symbol error probability will keep on going. So, a straightforward derivation, if we understand the Ps phi, that conditional error probability is given by a Q function, where actually the symbol energy by the total noise power spectral density is given. And if we utilize this equation 1.37, which where actually we have ended up with the computation of the variance from the jamming signal, if I substitute, I will get some expression of the power spectral density contributed by the combined effect of the noise as well as of the jamming signal. So, which is given by NOE phi, but NOE phi can be expressed like this, where N0 is the one sided power spectral density of noise, NOE is the one sided power spectral density, combined power spectral density of the noise as well as the jamming signal, and this equation is straightforward carried forwarded from equation number 1.37. So, here your interest is, and from using this equation 1.39, finally, we would like to see what is the expression for Ps, but before entering there, remember when we decided to, when we ended up with this kind of the variance calculation, we thought that the chip waveform will be rectangular type. Remember, whenever we have come from here to here, we considered here definitely that the chip waveform will be substituted by the rectangular one, apart from the consideration that integration will be done and some trigonometric knowledge will be applied to solve the equation 1.32. So, that is why all the expression that we have derived till this variance computation, it holds good only for the rectangular chip waveform. So, let us revisit little bit before proceeding further on the computation of the PS. What will be the situation if I utilize a sinusoidal waveform? Going back to the immediately module that we have discussed last, we have shown what will be the chip waveform design in case of the sinusoidal case, and straightforward plugging in the expression for the sinusoidal waveform here in the equation, we are ending up with the computation of one sided power spectral density of this interfering signal in case of the sinusoidal chip waveforms. So, the expectation, this 8 by pi square, the contribution will be actually very important to consider, and we will see the effect of these two different chip waveforms on the error probability calculation graphically in this module later on. Now, if we consider this capital G is equal to T s by T c, where T c is actually fundamentally by T s by T c. So, if I substitute these values, then we will be able to see that there is a exhibition of reduction of the interference power by a factor of G. So, from where the interference power will be totally substituted by, will be reduced by a factor of G compared to the symbol when we are putting only the value of the T s and we are computing the noise power spectral density, and if you put T c is equal to T s by G. So, this power spectral density will be directly divided by capital G. So, the processing gain that you will have in the receiver design or in a spread spectrum communication system, that will help you to bring down the effect of the interference by the processing, by the G times or by the processing gain times. That is proved also by both the equation 1.40 and 1.41 compared to the conventional system. In conventional system, the same equation hold good, but you consider T s instead of the T c, and here your whole period is getting divided by the period of capital G. So, we claim that this kind of structural communication system has high resilient, they are high resilient with respect to the jamming signal compared to the conventional communication systems. And if I compare this 1.41 with the previous 1.40, I mean the power spectral density compared to comparison is carried on by the sinusoidal chip waveform and the rectangular chip waveform. You will see because of this pi square by 8 effect that is coming here because of the chip design itself, you will be gaining around 1 dB advantage when your difference is equal to completely 0, and this at over what, over this rectangular chip waveform. So, this gain is coming with respect to your rectangular waveform. So, this observation was there in the earlier module, where when actually f d was equal to 0, exactly this portion we derived in the last module. So, here this is repeated just, and remember this advantage of getting of 1 dB will be gradually decreasing if we increase the value of f d equal to 0, we increase the value of f d from 0 value. So, as f d is increasing slowly, so this advantage of getting from the pulse shaping, whatever the advantage you are getting, slowly it will decrease, and ultimately you will not be able to see any advantage if the f d is pretty large. Following the same path, we can actually continue the analysis with the multiple tones. Here we had the tone where the interference is there, we have considered is the single. So, we can keep on adding actually the tone interferences based on the how many number of the certain jammers are present following the same framework, but it will be little bit complicated. And the theta 1 that we have considered, the phase, relative phase of the jamming signal that we have considered in this equation, we modeled it as a random variable, which is spread over the duration of the 0 to 2 pi as we have seen, and it is uniformly distributed over that. If theta 1 is like that, then the modulo 2 character of cos 2 phi it implies that its distribution will be same as theta 1. So, phi can be considered to be uniformly distributed over this 0 to 2 pi also. If so, the meaning is that if theta 1 is distributed over 0 to 2 pi, because of the modulo 2 pi character of this cos 2 phi, hence phi will be having some uniform distribution of this whole duration. So, then now the going by the symbol error probability calculation and averaging it over the whole duration of our consideration 0 to 2 pi, basically it is same to the 0 to pi also. So, it can be going on from 0 to pi also. But remember, we understand that all the positive values, cos 2 phi takes all the possible values within the duration of 0 to pi by 2. So, to shorten the integration interval, this integration can be equivalently run over 0 to pi by 2, what we have shown in equation 1.42. Now, this is the time to compare the performance of this nearly exact and the approximated values and the effect of the on the symbol error probability when we are disparate signal to interference noise ratio with respect to disparate signal to interference noise ratio. The signal to noise interference ratio is given by your GS by I, because your disparate signal is having a gain of processing gain of GA, and this was the interference power actually added at the receiver front end. If I consider that the value of the G is equal to 17 dB and the other values are considered like this, where the difference was equal to 0 and ES by N naught was given by 14 dB and 20 dB considered both. So, we are here. What is the understanding is when the bit error rate was equal to target bit error rate was 10 to the power minus 5, the approximate one was derived following these equations. Whatever we have computed in 1.42, considering the corresponding pulse shape, and the pulse shape even if it either 1.40 or 1.41 you have considered, and put the values of the PS phi here to compute PS. If you go by that, then you will be ending up with the dotted lines, approximate one, and nearly exact whatever we have already discussed in the last module. The fundamental equations, if we follow all that, where actually tone is exactly on the FC, and we have derived all that. If I put that value and if we keep the ES by N naught varying from 14 dB to 20 dB, then we will be seeing this kind of the comparison between the approximate model that we have developed here and the nearly exact model that we have developed in the earlier case. So, what is the observation is, for 10 to the power minus 5 target bit error rate for the data communication, where we are mostly interested in, we will be able to see that this approximate model and the nearly exact model differs by an amount of approximately 0.1 dB. That difference is really small, even smaller in case of your lower SNR values. So, we can actually confirm that the model that we have developed here in this discussion matches nicely with the close to the exact solution, and this example provide the evidence that the Gaussian approximation will introduce actually severe error, if actually the value of the G, I mean the processing gain, is less than 50. So, if for a high value, tremendous high value of the G, this difference that you are seeing actually it won't be there. See where we have considered this G, we have considered the G to approximate the variance of this V1 to be Gaussian. So, if this G is not tending towards the infinity, the J value of the G is really not high, central limit theorem does not hold good, and if it does not hold good, so this approximation that this V1 will be Gaussian does not hold good, and if this is not Gaussian, then the V won't be having a Gaussian distribution, and so the difference here that you will be seeing, that approximation that we have done over capital G, and hence the error probability we have derived, that will have a much larger difference compared to the nearly exact situation. Experimentally, it could be found that for the G greater than equal to 50 values, this graph will be close to both the graphs will be close to each other. So, to hold the conclusion is that to hold the Gaussian approximation, choose the processing gain at least greater than 50. And another important part is that one part the rectangular chip corresponding to the gain due to the rectangular chip waveforms corresponding to the sinusoidal chip waveform, all the gains that we have learnt in the last module, the gain from the chip design itself also hold good here. Another 1 dB improvement is possible maximum if you choose a sinusoidal waveform. So, this is actually considering the graph that we have shown here considers that both of them are using the rectangular waveform. So, if you utilize then another one is the rectangular, and with respect to the sinusoidal waveform, actually if you utilize, you will get another 1 dB improvement here. So, it will come below the nearly exact, but in that situation you should also develop the nearly exact graph with respect to the sinusoidal one. In both the cases, approximately the gap will be, if your G is pretty large, your gap will be within 0.5 dB for a target BER of 10 to the power minus 5, which is observed. So, here is the solution that if we choose a large processing gain, then even if actually our tone interference is not exactly on the center frequency, but it is really close to the center frequency of transmission, the deviation on the error probability will be hardly affected by 0.1 dB to 0.5 dB, which is not that much important. But remember, if G is less or your FD is your difference is increasing between the FC and F1. So, in both the situation that approximation does not hold good, and if FD is equal to if so large that wideband filter can simply cut out your jamming signal, in that situation also you will be leading down, there is no effect at all once again, and you will be governed by the symbol error probability calculation that is shown earlier by the classical or the conventional communication system.